Lesson 24. We will be able to quantify current and explain how it links to charge. This is a continuation of what we've been discussing the past couple of days. What we've been talking about is essentially this idea here, charge. Now, if you understand what charge is basically we take a comb or a brush or something and we brush away all the electrons from a rod, then that charge becomes positive. That can do some things. It can induce a charge in a piece of paper because essentially all the electrons in the ground will move into the paper, which will then move it. That is induction, and that leads to a movement. Then what we did is we talked about, well, if you get a big enough charge, you can actually create a jump of electrons from one place to another. And as those electrons jump, that discharge, we would call that electricity, because electricity is all about the movement of objects. Now, as these electrons jump over and they get discharged and they leave from one place to another, we then talked about well, how can we quantify this charge? How can we talk about it? We said, well, we're going to use the charge. We're going to measure charge in coulombs, and it has the symbol Q. We said that, you know, you have a lot of coulombs, and that means you've got a large amount of charge that's moving. You've got a small amount of coulombs, you've got a small amount of charge that's moving. Then we talked about insulators and conductors. That was about it. And then we said the reason is that a circuit works is if we imagine this now, and we just said, well, what if we put, like, in this jump, what if we could somehow, between the negative ball and the positive ball, what if we could put, like, something like, I don't know, like a light switch, like a light bulb? That would then create a circuit, and we could then use that power as it jumps from one place to another to gain light, and so on and so forth. Wouldn't work for forever, because eventually this guy would lose so many electrons that it would become positively charged, which is usually why we introduce another cord here. So what I want to do now is I want to talk about current, which is how can we, like, explain this movement of charge in a different way. So let's jump into explain that current in a different way here with this guy that we're going to talk about. So this here is Andre Ampere. Now, what Andre Ampere did was Andre Ampere essentially made, essentially what he was talking about is he talks about current flow. He was able to sort of quantify current flow. Now, what he did to quantify current flow is he said, current is the flow of electric charge. It has the symbol I. Now, I don't know, I think they use the symbol I because of some Latin word, but it doesn't really matter. Here, because he used the word amps to measure his current, or amperes. Either or would be good. And what he did is, and this is the formula that's probably really important, 1 amp is 1 coulomb per a second. So essentially, current is equal to the charge divided by the time. The idea that we're trying to say is, if you have a large amount of charge moving in a very short amount of time, like you've got a very, very quick speed, we would refer to that as having a high current. The opposite would be true if we had a low amount of current, or we had that current moving in a very, very slow speed. We would say that charge moving at a very, very slow speed, we would say that's a very low current. So this is our idea of current.
4 is our number.
Okay. Good. Let's have a look at a quick question here, just because we'll get some work done here. How to do it? I'll open up chat as well. I want you guys to throw in your answers here as we go, but we'll do a quick one here. 22 coulombs of charge passes down a wire in 8 seconds. I equals Q over T. So Q in this time, or what charge? For 22 coulombs. That's some amount of electrons, okay? Some huge amount of electrons is going down a wire. And it takes those electrons 8 seconds to get down that wire. Or perhaps 22 coulombs of charge pass through a single point in 8 seconds. That's a fair bit of charge. It's a fair few electrons jumping through a particular part. If I go 22 divided by 8, it's going to be 2.8 something, but I'll just do it. .75. So we've got 2.75, right? And because this is current, we're going to measure these in amps. 2.75 amps. We can just write A. We don't write lowercase a, we write capital A. 2.75 amps. Beautiful. How many electrons pass through in 1 second? All right. Well, okay. Let's just quickly do this, I guess. Well, to work out how many electrons, we really need to know the charge. So I equals Q over T, which means that IT equals Q. So if I've got 2.75 amps times 1, that means I've got 2.75 coulombs. But that's not the answer. If I've got 2.75 coulombs, and I know that the charge on one electron is 1.6 times 10 to the negative 19 coulombs, I can use that to work out, well, how many of these electrons fit into here? How many electrons are they going to be? 2.75 divided by 1.6 times 10 to the negative 19 gives us 1.72 times 10 to the 19 electrons. Yeah, I just wanted to quickly, so, yep, sure. So this is the general idea of how we can calculate current. Current isn't, and let me just go back over this again. Current is a measure of charge. Current is a measure of charge per time, okay? It's almost got to do with the speed. And we're going to talk about the difference between a small current and a large current a bit more now. But before we do that, I've got one more example. Hold on. I wanted to talk about this, milliamperes. Now, a milliamp, if the current on a wire is 250 milliamps, how much charge will pass down the wire in 2 minutes? All right, let's talk about this firstly. What is a milliamp? So a milliamp is a thousandth of an amp. So if I have 1,000, 1 amp is equal to 1,000 milliamps. So 250.
When you do AirDrop and your phone is connecting to another phone, you have a de-anonymized way. Like I don't, when you look in your phone, you can see that your phone is connecting.
Sorry, I just muted everyone. Okay, so if I've got 250 milliamps, right? that's going to be 250 milliamps is going to equal to 0.25 amps. It's very, very similar between grams and milligrams, essentially. So if I wanted to use this formula, I equals Q over T, and this time I want to work out the amount of charge. So again, Q equals I T. So now if Q equals IT, I was going to be 0.25 times, sorry, my printer has decided to wake up for unknown reason, times the time. This time they've given me the time as 2 minutes. I can't use 2 minutes. I have to change that. So 2 times into seconds. 2 times 60 is going to give me 120 seconds. So 0.25 times 120, that'll give me how many coulombs of charge pass through, which is going to be 30. Thanks, Brendan. You were faster than my calculator. Mostly because they couldn't find it. 30 coulombs of charge. So that just quickly, so that we can see what this means. The charge is in, when you use a charge in milliamps, you've got to divide that by 1,000 if you want to use it in a formula like this. Consequently though, if you do get an answer, let's just say you're doing a formula and it was like, oh, you know, you've got 0.5 coulombs of charge goes through a wire in 10 seconds. And and you work out, oh, well, that's going to be 0.05 amps. If you want to write down, instead of 0.05 amps, if you want to write down 50 milliamps, then that's fine too. This one would be the one on the right. That's what we would prefer if we were doing circuits and stuff, because it's like a lot of currents and circuits are measured in milliamps. Both of them are correct though, so don't think you'll get the answer wrong if you do the one on the left. But I'm just sort of showing you, you can do it different. Let's talk about, so now I'm going to talk about different size charges. Current is the movement of charge. It doesn't have to be through wires. Now, this is one of those ones that lightning is a current of moving charge through air. Nerve impulses have small amounts of current, and ions moving through salt solution make a current. Ultimately, anywhere where charge is moving, you can refer to it as a current. Because what you're doing when you say, well, what is the current? You're saying, well, how quickly is the charge moving through that nerve? How quickly is the charge moving through the air? How quickly is it moving in the salt solution? Is it fast or is it slow? So that's really what I want to talk about when I talk about current. I also want you guys to, every time I talk about electricity, you guys are going to have in your head, oh, we're talking about wires, we're talking about circuits. Don't just think about that. Try to understand what the concept is on its own. Remember, a charge just means electrons, or an amount of electrons, an amount of charge moving from one place to another. So obviously in the nerve impulse, we're going to have a very, very small amount of current. Not because it's moving very slowly, because at Q, the amount of charge is going to be very, very small. We're going to only have a small amount of electrons that are actually moving. Whereas lightning is going to be very, very large, because we're going to have a large amount of charge moving in a very, very short time. Because ultimately, lightning can be done in a matter of seconds. Okay, so when we talk about charge, we're talking about how quickly it's moving, how much of it is moving, and how quickly it's moving. So let's talk a bit more about low versus high. So obviously in a low current situation, you've got some charge moving, but you haven't got a lot of charge moving. You've got a little bit of charge moving in pretty quick time. Whereas a high current, you're going to have a lot more charge moving. You're going to have a lot more moving at one time. And so therefore you'll usually need, for a high current, you'll need a much larger wire, because you'll need to, and if you think about lightning compared to, I don't know, say a nerve, because you've got so much charge moving, it takes up a lot more space. And that's because there's more electrons. And the reason there's more electrons is because there's more charge. That's the basics of it. High current means there's more charge, means it's more electrons. You need more space. We can even use an example like this. I thought this picture was kind of interesting. Grab a look at these. These are like, we've got here about 7 or 8 different wires. On the far left, but down the bottom was the part that I found interesting. Down the bottom it says their maximum possible current they can take. So this small current can take 20 amps, which is a fair bit actually. You can get current like even smaller wires than this. But yeah, this can take up to 20 amps before it starts to have issues. If I look at these next ones, then we've got like 25 amps, then 30 amps, 40 amps, 55, 95, 125. And by the time we get to 125, we've got a thick ass, like, you know, copper wire. This guy is really thick. No jokes intended, but it can take a lot of current. And again, go back to the lightning example here. This is a large amount of charge moving very quickly. And when we've got a large amount of charge moving very quickly, it takes up a lot of space. And that makes it a high current, whereas something that is moving slowly or only has a very small amount of current will probably be will have a low current. So sorry, I got that wrong. Something with a small amount of charge moving slowly will have a low current. Usually electrons don't move slowly, so usually a low current just means low charge, very few electrons, small thin wires. So what do we mean by current? I usually use this example just because I like to quickly explain what it means. Yep. So what we're talking about here is a tank, which represents in this case a battery. It's full of energy, and then we've got a pipe, which is going to be our wiring, and a tap. In this case, the tap is closed. We know if the tap is closed, there is no interest for the electrons to want to go around the circuit because they can't get to the positive. In this case, and this is why we're going to use this example a lot, there isn't any want for these the water to flow out of the tap towards the ground because it can't get there. So because the water can't get there, it doesn't flow. We're going to use this a couple of times to refer to circuits and how they work. So ultimately, when the tap switch is off, is there any flow of current? Can I get a yes or a no? Is there any flow of current when the tap is closed? Let me know on chat or out loud, up to you. I've muted you, you can unmute yourself. Is there any current? I've seen the number 30.
No.
No. Beautiful. Nope. There's no flow of current because there's no movement. There's no movement of charge. If there's no movement of charge, there is no current. Now, when I open the tap and water starts flowing out, then yes, then there is a current. Okay, the electricity can move, the current can move, the well, not exactly the current, but the charge can move. The charge can move, which means there is a current. We're not going to talk whether or not that's a high current or a low current, but remember, all we talk about when we're talking about current is moving charge and how quickly they're moving. In a circuit, when the switch is off, there is no current. when I turn the switch on, now there is a current, because now the charge can flow from the negative, from the current. The current, of course, can now flow because the switch is open. The electrons have a reason to move. Now, the last sort of parts that I want to talk about current is last bit I want to talk about current. I haven't got too much time left, as you guys may have seen. I want to talk to you guys about the different ways we refer to current. So I guess the two things we talked about so far is, one, how to quantify current, I equals Q of T, and then I've also just done what current means. Essentially, high current means a huge amount of charge moving very, very quickly. Low current means a little bit of charge moving slowly. And we can measure that in a wire. If we could imagine that you were an atom on a piece of copper wire, you could count the amount of charge that is moving past you and how much of it moves past in 1 second, and then that would be your measure of current. But there's one last topic I wanted to talk to you guys about current, which is how we define current. So back in the day, this is not on the slide, but back in the day when we were discovering current, what we tried to do is we tried to figure out, well, what was moving. And the problem that we have is our dear scientists thought back when we started off that it wasn't the electrons that were moving, it was the protons, the positive charges. Because remember, we can't see this stuff. We're going to try and guess. So what they said is, well, we're going to call this conventional current. They said conventional current assumes the current flows out of the positive and into the negative side of the battery. This convention was established when electricity was first discovered. Now we know this is not how it works. Mostly because I've talked to you guys about how charges move, how the electrons are doing the moving, the protons are too big. That's what we discussed. So this is not the way things actually work. It's not correct. What is actually happening is the electrons flow out of the negative side of the battery and into the positive side. So we've got these two terms here, conventional current versus electron flow. Now, the direction the current flows does not really actually, here's the part that's the kicker. The direction the current flows doesn't really affect what the circuit is doing. It doesn't really make a difference which one you use as long as you are consistent. Ultimately, what I mean by this idea at the top is if I have a circuit and it has a light bulb in it, I'll do a little switch here. It doesn't matter whether the electrons are going this way or whether the electrons are going this way. The light bulb will still switch on. So for a lot of devices, it doesn't matter. There are some devices like LEDs, which are polarized, which it does care about which way the electrons go through. But for most circumstances, it doesn't matter which way we move the electrons through a circuit. So therefore, you've got to realize it sort of is important, but it's also not really. Now, both of them are used. Like we do use both of them in science. However, usually what we use is conventional current. And like for electronics and science, we would use electron flow if we were dealing with like actually shooting electrons, because you can do that. You can actually shoot electrons in electron guns and things, or whether you're building up a negative charge somewhere. But for most cases, we're going to use conventional current, which is sometimes for some of you might be weird. Because you might be like, but it's wrong. But I would agree, but that's just the way that we measure things. So really quickly, correct conventional current is the direction of current from the positive end of the circuit to the negative end, whereas electron flow is the direction of the electrons move from negative to positive. So it's the other direction. And we use both, but we will tend to use, whenever I draw a circuit, that's why when I drew this circuit here, notice how I drew the electrons moving from the positive into the negative, because that's the direction the current moves, even though that's not the direction the electrons are moving. Okay, so I've got about 2 minutes left. I think I'm going to run out of time, but I'll quickly talk about these last little bits. Quick reminder for you guys that haven't done it, you need to answer the attendance question on the Google Classroom. If you haven't already, go back and do that. Last 2 minutes, I'm going to quickly talk about amp meters or ammeters. Ammeter allows the current to be measured. So how do we measure these currents? We use an ammeter. Ammeters have very, very low resistance, and so as to not disrupt the movement of electrons, because we don't want to have a high resistance, because then that'll kind of screw around with the circuit. These can mean that they can potentially create short circuits, and if this stuff down here doesn't make sense to you, that's okay. We haven't explained what a short circuit is. We haven't explained what resistance is either. I'm just trying to tell you that, but the ultimate idea with ammeters is they're designed to measure the current without, messing around with the circuit. This is how you draw them. You use the letter A, and this is what the old type looks like. Yes, we still use a fair few ammeters at the school. We haven't embraced too much digital stuff yet. But what do the digital ammeters look like? What does a digital current reading look like? Ammeters, this is exactly what I just said. That's the symbol for it. An ammeter is connected in series. It has a resistance, so the circuit isn't affected. It has low resistance, the circuit isn't affected. They must be connected like in series, but we're going to explain that later on too. And the last bit is the modern way we do things is with the digital multimeter. These guys have two sections, a black wire that's connected to the negative and a red wire that's connected to the positive side of what you're trying to measure. They can measure current, resistance, voltage, and continuity, so they can actually measure a lot. So this is what most electricians would use instead. We're about to run out of time, ladies and gents, so I'm going to stop it there because of